Okay, welcome to lecture here. Last lecture. Okay, today, since it's sort of the last day, I'm just gonna kind of go over maybe some of the chapters, some of the topics that we talked about, just as sort of like a little review. And be pretty open, I think, today and tomorrow. Again, tomorrow is our final, and our final will be taken pretty much like our normal exams. It will be taken around lab time, so around 9:30-ish, like when we normally sort of kind of start our exams, is when our final will begin. So for today, mainly going to be just some review, sort of open to some of the topics that we talked about, just some, maybe also some of the early stuff that we did at the beginning of the semester here, just to, again, remind everybody of some of the important things that we sort of covered. All right, so with that being said, let's kind of start with that. So we first started talking about in this semester really the structure of the atom, really, and we started with the atom first here. And remember, again, ultimately there was a lot of experiments that were done, by people like Thomson, who used the cathode ray tube, people like Milligan, who did the oil drop experiment. And you remember there was sort of the early model of the atom, which was that plum pudding model, where they was thought the atom was basically a sphere of positive charge spread out. We had negative electrons embedded inside. Most of the mass of the atom was thought to be the electron. And, it's just sort of the accepted model, from those earlier experiments, again, done by Thomson, Milligan, and some others as well. And, this was sort of later kind of had to be thrown out after Rutherford, right, did the gold foil experiment. And with that gold foil experiment, we sort of got our modern sort of version of the atom, where basically the atom is mostly empty space. It contains a nucleus, and as we talked about, nucleus is where we have our protons, which are positively charged. We have our neutrons, which have no charge. And out from the nucleus at some point is electrons, right, which are negatively charged, kind of flying around. So we have our nucleus here, which has our protons and our neutrons. We have our electrons. And as we talked about on several different occasions, again, those electrons are moving pretty randomly about the nucleus at some distance, again, within that empty space, which is sometimes referred to as sort of the electron cloud. As we talked about, there obviously is some attraction between the nucleus and the electrons, which is pretty much a hallmark of sort of chemistry, and a lot of principles in chemistry is the idea of the electrostatic attraction, like that opposites attract. So electrons being negatively charged, the nucleus being positively charged, again, going to have some attraction between those two. So as we talked about in later chapters as well, that's, what accounts for what electrons, for example, are involved in bonding, which ones are not involved in bonding. Really, their sort of distance, if you will, from the nucleus is really important in that. The other major sort of movement away from the plum pudding model, as we talked about, was the idea that most of the mass of the atom was made up of this nucleus. And that's because, if you remember, out of those three subatomic particles, the proton, the neutron, and the electron, the neutron is the heaviest out of all of them, with the proton being pretty close to it in terms of mass. And both of those things, the proton and the neutron, they're both about 1,800 or so times heavier than any electron that's present, and thus because the proton and neutron are in the nucleus, they do make up pretty much most of the mass of the atom, with the electron again being least massive out of all three of those, and again traveling in that sort of empty space. Now, we also then talked about some important properties sort of atoms as well, and a couple important things that we talked about, which was the atomic number. The atomic number is the number of protons you find in an atom. And remember that the atomic number is found on the periodic table, and it is that number that is typically up on top of the symbol when you look at it. And the other important thing about the atomic number was that if it is a neutral atom, then the atomic number, which is the number of protons, will also tell you the number of electrons that are present. So again, the atomic number's definition, though, as we talked about, is that really just the number of protons, but it will secondarily sort of give you the number of electrons if it is neutral. If it's not neutral, as we talked about, you do have to adjust the electrons based on the charge that's present. The other important number that we talked about in relationship to this was the mass number. And the mass number is the number of protons plus the number of neutrons that are present. And the mass number is not found on the periodic table. So remember that the number on the bottom here is not the mass number, but that is the atomic mass. So you cannot find the mass number on the periodic table, just the atomic number. But if you have the atomic number and the mass number, the benefit of both of those is that if you take the mass number minus the atomic number, gives you the number of neutrons. So the number of neutrons can be found by really taking the mass number minus the atomic number, and you do that. When you calculate those things, as we talked about, when you calculate those things, they all should be positive whole numbers. When we talk about the number of protons there are, neutrons, electrons, the atomic number, and the mass number, again, should all be positive whole numbers when we sort of calculate those things. And in these problems, as we talked about, you typically should have enough information given to you to be able to calculate those guys. We can also write these guys sort of with their isotope symbols. Remember that isotopes, we also talked about here, isotopes are the same element, but different mass. And remember that in order for them to be the same element, it is the atomic number and really the number of protons that determines what element we're speaking of. Because again, as we talked about, if you look on the periodic table, every element has its own unique atomic number, which means the number of protons is the subatomic particle that really determines what element we're dealing with. So in order for them to have different masses, it's really the number of neutrons. So they typically have different numbers of neutrons. And thus different mass numbers as well. And when we write those guys, we can use the symbols. So like we could do chlorine, and then again on the bottom left is where we put the atomic number. So the atomic number for chlorine is 17. And say we had, we'll go with 27, make the math easy. All right, so up on top is where we go with the mass number. Bottom number, again, our atomic number. And sometimes these are also written something like this, Cl27, again, this being our mass number if it's written in this sort of form. But usually this is the form that we do, mass number top left, atomic number bottom right, And again, from that, we can know that in this particular case, we would have 17 protons because of its atomic number. Again, there is no charge here. Because there's no charge, then that means we also should have 17 negative electrons to balance those out. And if we take 27 minus 17, which is our mass number minus our atomic number, we get 10 neutrons in this particular case. Again, as we talked about, if we do have something with a charge, which is a cation or an anion, depending on whether it is positive or negative, we do adjust the count there. And again, the only thing that's going to change is the number of electrons. So here we would have still 17 protons because it is still chlorine, but now we have one more electron here. Negative means that we gained electrons, and it would have 18 electrons. Again, 17 positives, 18 negatives gives you that -1 left over, and we would still have our 27 minus 17 in this example for 10 neutrons. So we talked about writing those atomic numbers, mass numbers, figuring out the number of protons, electrons, and neutrons. And again, those were important things to determine. And again, as we talked about, pretty much the thing that most people mess up on this deal is that mass number. Again, for some reason, people always want to go to the periodic table and use that number on the bottom. And again, remember that that is not the mass number. That is, again, just the atomic mass, which deals with the mass of the protons, electrons, and neutrons. And what often confuses people, like we talked about back then, again, is this idea that it is very similar in terms of their numbers, but the easy way to remember that is, again, they all need to be whole numbers. So if you look on the periodic table, pretty much everybody there is not a whole number, you know, in terms of the bottom number, the atomic mass, so they're all decimals. So that's a good way to remember, hopefully not to use that. Then we got into sort of the conversation about really electrons in the sort of the second chapter there. And we started talking about electrons and really sort of their movement from one level to the next and sort of how they move and stuff like that. And that brought us into a conversation about waves. And when we talked about waves, remember that waves, right, is basically the movement of sort of energy through space. And there is, you know, the wavelength, right, which is sort of your distance between two peaks or a trough. We also talked about frequency, which is the nu, although people call it the V there, but that is our frequency. And we also talked about C, which is the speed of light. Which is a constant 3 × 10⁸ meters per second. So we got into some conversation about sort of waves and sort of relationship of waves and energy. And what we saw was that the longer the wavelength, the longer the frequency would be. And that usually results in lower energy waves. While if you have a shorter wavelength, usually a faster frequency, I guess higher is the better word there, higher frequency, that usually results in a more high energy wave. So again, something spread out like the top guy would have probably less energy than somebody like this, which obviously is occurring, you know, a lot of fashions very quickly. Frequency, right, in terms of units of frequency, reciprocal seconds is a common unit, and remember, are a hertz, and they are basically the same. So reciprocal second is the same thing as a hertz, and those are two very sort of common units of frequency that we see. We also saw sort of an important equation that goes with sort of waves, right? And for waves, basically the speed of light is equal to the wavelength times the frequency. And in terms of units here, the wavelength is typically in meters. Our frequency is usually in 1/seconds. And that's why when we do the speed of light there, it is meters per second in terms of the units that is associated with this. So this formula here does allow us to really rearrange this and connect and solve for any of those things, the wavelength or the frequency. So if you want the wavelength, it is the speed of light divided by the frequency. If you want the frequency, it is the speed of light divided by the wavelength. So these are a few different sort of rearrangements that we could do. And again, some very sort of common units that our formulas, rearrangements that we use are sort of these guys. Also, speaking of units, you know, a lot of times, sometimes waves, especially in the visible part of the spectrum, again, is given in the sense of nanometers. And nano, right, is nanometers, for example, is 10 to the minus 9, right? And again, that means that there are 10 to the minus 9 meters in 1 nanometer. And again, that's a very common sort of conversion factor that's used, especially it's dealing with waves and wavelength. One sec here. So we talked about those guys there, and sorry about that. So knowing how to solve for those obviously is very important in terms of wavelength, frequency, and calculating those things. We also talked that we basically what we're talking about here a lot of time in this chapter is that idea of basically electrons, and electrons going from a lower state of energy to a higher state of energy. And as they try to relax back down, again, they want to usually be in that lower state of energy. They do give off that energy in the form of a wave, and that's sometimes what is referred to as a photon of light. We can sort of tie together those equations that we just saw, which was our C is equal to the wavelength times the frequency, with our energy equation that we saw, which is the energy is equal to H times the frequency, H being our Planck's constant, and that was our 6.63 times 10 to the minus 34 joules seconds. And the tie-in here is if we solve this guy for frequency, as we saw, it is C divided by the wavelength, which means the energy would be hc over the wavelength. And this sort of version of it is really helpful because obviously it allows you to calculate the energy associated with a photon by simply just knowing the wavelength, as both h and c are constants, which means if you know the wavelength, you could calculate the energy. And if you know the frequency as well, by using the original equation here, you could also obviously be able to calculate the energy associated with it. So again, this sort of substitution version here is something that we see a lot when we did those problems, sort of using that relationship. And we also talked about the idea of the electromagnetic spectrum. And the electromagnetic spectrum, right, is basically sort of different areas. You know, we have gamma rays, we have X-rays, we have UV, we have the visible part of the spectrum, we have some infrared, we have some microwaves, we have some radio waves. Yes, so everything that you were given on previous exams will also be given to you on the final, if you need it, obviously. But you know, whatever you need in terms of constants, conversions, you know, any type of solubility table, you know, those type of things would be given to you, just like you were given on regular exams. So all those things would be given. And this is an electromagnetic spectrum, as we talked about. And again, in terms of wavelength, this is very longer wavelength on this end, shorter wavelength over here. And as that relationship, as we talked about, that means this is lower in energy on this side, and this is higher in energy, over here as well. And again, as we sort of move in this direction, again, it's getting more energy to do different things. Radio waves, not too bad. Microwaves, again, enough energy to kind of spin water molecules really fast to heat up our food. As we move into the IR, that's really for heat. Ultraviolet, much stronger in energy, why we put sunblock on. X-rays, right, why people leave the room. And gamma rays is really just pure radiation or radioactivity, very high in energy. And a lot of the time we did focus in on sort of this visible part of the spectrum here, and that's where we see our, Roy G. Biv, right, the colors that we see. So if that energy comes off in a wavelength somewhere in this region, and again, this is the region where typically sort of the wavelength of those guys are given in nanometers. And again, this is our Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. Although in terms of really wavelength, red is actually over here. And kind of blue or violet is, sort of on this end as well. So again, red having a longer wavelength and lower in energy than, say, the blue violet on this side, which would have a shorter wavelength and a higher energy. So although if we write it that way, it actually goes this way, or Roy G. Biv, in terms of energy as well. So again, as these electrons, and sort of the relationship that we talked about was that these electrons, as they again transition from sort of one energy level to the next, they need to release that energy in the form of a photon. And again, it may fall in this visible part of the spectrum where we could see color. So there's a couple of experiments at the very, very beginning, like the flame test. When you do that, obviously you're adding a lot of energy. It's exciting the electrons. And again, depending on the elements that are present, as those electrons relax, they give off that energy, and a lot of that energy is in the visible part of the spectrum. So we see the typical color for a particular element happen. Same thing with that electron discharge tube. Again, when you excite those electrons by putting on the electrical current, same thing happening with those electrons, going to be giving off those colors. And the thing that we talked about in terms of sort of elements is, if you look at it through, say, a spectroscope or a diffraction grating, basically what happens is they separate out into these specific guys, which are known as line spectrum. And line spectrum happens for elements. Basically, they sort of only allowed transitions of those electrons occur, and we get those guys. And that's different than sort of a continuous spectrum that we talked about, where pretty much everybody's coming off at once. So more of a rainbow type of effect. You have wavelengths coming off at all different wavelengths at once. And that was sort of that idea that, kind of in terms of energy, is that word that we heard a lot of, which was quantized. And quantized, again, is that idea, sort of the very simple idea of like a staircase, right? So when we talk about electrons and sort of acceptable levels for where they're at, they're either sort of on one energy level or the next. They're not somewhere in between. So they do gain energy in the form of this quantized packets of energy, which is related to this E equals H times the frequency, which means, again, the electron will either be on this energy level, it will gain enough energy to get to this energy level. If it drops in energy, it will have enough to get back to there. We just won't have sort of, the idea there is we won't have like a floating electron between energy levels. Again, they're going to either have enough energy to go all the way up or all the way down to a particular energy level. And that's sort of the idea of quantized. Again, related to the stair example, as we talked about, if you're going upstairs, you're going to have enough energy to get to this step, or this step. Most people don't go, I'm going to stop, halfway between a step, because you'll probably fall, right? And that's sort of the idea here of that quantized energy. We also talked about that we could actually figure out sort of the energy associated with electrons as they transfer. And that, sort of the early idea of an atom, or how electrons sort of transfer, was that Bohr model. And remember, the Bohr model was sort of that planetary model of the atom, where you have, your nucleus here, and you have these electrons in these pretty orbits that are just kind of, you know, going around and around sort of in these pretty circles. And again, either they are here or here or here. And that really described nicely sort of the lines that we saw in hydrogen. But as we talked about, it sort of fell apart as you moved away from hydrogen. And there was sort of an equation to calculate that, which was the change in energy is equal to minus 2.18 times 10 to the minus 18 joules, 1 over n squared final minus 1 over n squared initial. And n is that principal quantum number. Are really, as we've talked about, really the energy level, right? And remember that n equals 1 is the ground state. That's the lowest in energy, closest to the nucleus. Anything above that, n equals 2 to the 7, or what is sometimes referred to as excited states. And those are higher in energy. And this 2.18 times 10 to the minus 18 is a constant. That's the Rydberg constant. And again, that's a constant value. So we could use this to calculate the energy associated as an electron transitions, for example, from, say, the first energy level to the second, maybe the third energy level to the first, or so forth. And when we talk about these electrons sort of transitioning, we talk about a little bit about energy. We don't talk a lot about energy in this semester, which we don't usually. But energy in the sense of absorbing energy is endothermic, and giving off energy or releasing energy is exothermic. And in terms of numbers, when you calculate energy and get numbers, typically endothermic values are positive values, exothermic values are negative values. So as an electron goes from, say, the first energy level to the second, that is an endothermic process. Energy has to be given in or absorbed by the atom to allow the electron to transition upward. But as it goes back down the other way, it would be exothermic. It has to release the energy coming back down. Again, the atom would release that energy. And that's why sometimes we will see positive numbers here, depending on which way that transition is, or negative numbers here, depending on which way that transition is. And that's also an important sort of relationship, because we can tie, you know, really that equation up there to our h times our frequency, or hc over our wavelength, you know, will equal really this as well, 2.18 times 10 to the minus 18, or 1 over n squared minus 1 over n squared initial. So remember that you can sort of tie all these together, which again, if you figure out the energy, you could also use that to figure out the wavelength that's of light that's being given off as those electrons basically transition. Also, speaking of the positive and negative sort of values that we get for energy, remember that if we do go back and sort of use you know, these equations together, we do want to get rid of the negative when we try to find something like wavelength. Remember that wavelength and frequency should be positive values. And sometimes when we use that energy value, we do get a negative energy, which is perfectly good for energy. So remember that energy should have really either that positive or negative value. Again, it indicates whether or not it's exothermic or endothermic type process. But once we kind of use that energy number to do a calculation for wavelength or frequency, we do sort of want to get rid of it because we can have obviously a negative wavelength or frequency. So that's that little thing again. If you remember, I think in one of the labs, you had a lot of that happening. If you get that energy value, perfectly good. You should leave the positive or negative on the energy value, but again, get rid of it when you continue on to calculate something like wavelength or so forth. We also talked about sort of the idea of De-Broglie, and moving away from Bohr's model that electrons really don't travel in these pretty orbits, that we really don't know at any given point in time sort of where an electron is or how it's traveling. We also talked about sort of the idea of like a standing wave with De-Broglie wavelength. And that was the wavelength in meters is equal to h over the mass times the velocity. And remember that when we use this sort of De Broglie wavelength, we do want to watch out for units. This is typically joules seconds. The mass here does need to be in a kilogram, and the velocity needs to be in meters per second. And the reason for that is a joule is equal to a kilogram meter squared seconds squared. I did that backwards, sorry. Meters, kilogram meter squared over second squared. Get rid of that, there you go. Which means if we put our units into here, technically we would have this unit here for the joules part of it. So that is a joule. And we would then have our seconds divided by our kilogram, which is our mass that needs to be in kilograms, and our meters per second. Again, kilograms will cancel. A second here will cancel. The other second will cancel. And 1 meter will cancel. And that leaves you a meter when it's all said and done. The good news is, I guess, h is a constant. So the value is still the same. So it's still the 6.63 times 10 to the minus 34. But that is, again, how those units sort of cancel out. So we talked about the idea of sort of moving away from the orbit model to this idea of we really don't know exactly at any given point in time where an electron is or how it's moving. So that's the idea of it. You know, it's pretty moving randomly about, you know, the atom and stuff like that. The best that we could do is think about probability. So when we think about probability, that's again moving away from orbits to that idea of orbitals, right? And we think about orbitals as sort of theoretical locations in an atom. Our probability maps really in an atom as to where electrons could be found. And if you remember, we talked about pretty much S's, P's, D's, and F orbitals. And depending on the energy level, you'll find some of these present, and some you may find them all present on a certain energy level. But in terms of how many there are, in terms of different types, there's only one different type of s orbital, as opposed to there's 3 p orbitals, there's 5 d orbitals, and there's f orbitals, 7 f orbitals. Remember that any individual orbital can hold a maximum of 2 electrons, which means, again, if we max out our S on any level, that's 2 electrons. That is 6 electrons, that's 10 electrons, and that is 14 electrons. And, you know, how we get to all these numbers and sort of what orbitals are on what energy level comes from another sort of important thing that we talked about, which was quantum numbers. And remember that there really are 4 quantum numbers. There's the N, there's the L, there's the M sub L, and there's the M sub S that we talked about. And really these are sort of the mathematical descriptions as to, you know, how we get to those different types of orbitals. So N is the principal quantum number, as we talked about. And as we talked about, that is essentially your energy level. And it does have values of like 1 through 7. L is the angular momentum. And, you know, it's sort of the, for the lack of a better one, you know, the actual shape are really the orbital type. And it could have values, L has values of 0 to n minus 1. Then we had M sub L, which is our magnetic quantum number. And really, you know, that's, for lack of a better description, how many orbitals there are. It really is sort of their orientation in three-dimensional space. And M sub L could go from minus L to 0 to negative L. And the last quantum number is M sub S, which is our spin quantum number. And that's basically the electrons in an orbital. And they do need to have sort of opposite spins, as we talked about, and basically it could be plus or minus a half. So for example, if we run through this here just real quick, just to remind everybody, if we do n is equal to 1, which would be your first energy level, your L value can go from 0 to n minus 1, which means 1 minus 1 is 0, which means the only value you could have is 0 for L. And because you have only 0 for the L, the M sub L actually has to be 0 as well. And the M sub S would be plus or minus 1/2. What that means is when we go to our first energy level, which is the ground state, so first energy level has a 0 for L, which represents a s orbital. So the only orbital that's found on the first energy level is a 1s orbital, the 1 meaning first energy level, s meaning the type of orbital. And M sub L means that essentially there's only one orbital. And plus or minus a half means that when we put our electron in there, the first one would go up, second one would go down. The one that is going down has a minus 1/2 for M sub S. And the one pointing up has plus 1/2 for the M sub S. And again, if we go to n equals 2, n equals 2 means that we could have values of L of 0 and 1, going 2 minus 1 is 1. So the S, as we just saw, is the 0. The 1 represents a P subshell. And for each of these individual guys here, we can have an M sub L. So this guy would be 0. For the 1, it could go from minus 1 to 0 to plus 1. And obviously, they both could have plus or minus a half in this case. And what that tells us is when we go to our second energy level, we also see a 0, which means there is an s orbital there. We also see a p orbital, which is represented by the 1. And we see that there, for the p, 1, 2, and 3 different p orbitals. And this is really the px, py, and pz orbital. Again, minus 1, 0, plus 1 for our M sub L going across there. And again, in each of these individual orbitals, we could put 2 electrons, one going upwards, which has the plus a half, and one going down, which has the minus a half. So if you remember, we could really, figure out the 4 quantum numbers for every specific electron that's present by doing that. And again, it gives us an idea as to how many electrons there would be perhaps on a particular energy level. Now, when we talk about these things, a couple other terms that, sort of came about when we talk about a level or a shell, that's like the, say, n equals 2. That would be like everybody that's contained there. And the maximum electrons there would be 2, 4, 6, 8 electrons if you filled it up. Now, if we're talking about a subshell or a sublevel or a subshell, like a 2p subshell, what we're talking about is specifically just these guys here. which would max out at 246 electrons. And if we're talking about just a 2p orbital, the maximum electrons would only be 2, because it would either be the 2 electrons in this guy, the 2 electrons in this guy, or the 2 electrons in that guy. So those are some common sort of terminology that we talked about when we were talking about sort of these orbitals, these electrons, and sort of where they're at. You also could very quickly, if you wanted to, for an energy level, figure out how many max electrons there are by using sort of this formula. So for example, n equals 2. 2 squared is 4. 4 times 2 is 8, which is our 8 electrons. Here, n equals 1. 1 squared is 1. And 2 times 1 is 2, which is the 2 electrons. So this is a sort of quick formula if you don't want to draw out all the arrows to figure out how many electrons you would have sort of maximum there if you wanted to figure out what's on a particular level. This then sort of tied into electron configuration that we talked about. And remember, electron configuration is the order at which electrons are filled into the atom. And we do that, we do it based on filling order. And remember that you can sort of quickly make that order by just going, you know, 1s, 2s, 3s, 4s, 5s, 6s, 7s. And again, as we just saw, first energy level is where S's occur. P's occur on the second. This is where they start to show up. And you just go down. D's don't occur until the third energy level. And F's don't occur until the fourth energy level. And you can make this sort of guy pretty quickly yourself. And remember, we kind of do this zigzag approach. And this gives you, again, the sort of correct order of how electrons get filled into the atom. We always start up here. Remember that the main thing happens here. We actually go from 3p to 4s and back to 3d. So the 4s orbital is actually lower in energy than the 3d. Electrons go in one at a time, again, into the lowest energy until they're filled, and then continue upwards. And again, that in conjunction with 2 electrons max for s orbitals, 6 electrons max for the p subshell, 10 electrons max for the d, and 14 electrons max there for the f orbitals. Will help you write really any electron configuration that you wanted to. So for example here, if we did, we'll do say sodium, which is 11. We look up sodium on the periodic table. Its atomic number is 11, which means it has 11 protons, also has 11 electrons if it is neutral. Starting at the top, that would give us 1s2, 2s2, 2p6, 3s1 as its electron configuration. We also talked about the idea that you can write what is referred to as noble gas configuration, because if we take this part of it, that is 10 electrons by counting up the top. And we could do something like neon 3s1, right? So that's a way that you could kind of do noble gas configuration. Take the noble gas that comes right before it and then continue on with the electron configuration at that point. We also talked about here as well drawing orbital diagram, which are boxes or lines that represent each of the orbitals that are present, and this not being drawn based on energy here, but just kind of being drawn. And again, in terms of how those electrons go in, first one goes up, right? Second one goes down. And I missed my 2s in the middle there. We'll put a 2s here to fill it in. Up and down, it should be here. And when we have options here, right, remember they go in one at a time in the upwards direction and then come back down and fill. And then it could go up there as well. And again, we could tie this to like we did our quantum numbers. So for example, if we want the 8th electron in sodium, what are the 4 quantum numbers? That's how you would have to sort of remember how it goes in. The 8th electron would be 1 this way, 2 3 and 4, 5, 6, 7, and 8 coming this way. And it's actually this guy. And that's important because he is heading downward. And what that means is he's in the 2p orbital. And that means that n would equal 2. And since n could equal 2, L would equal either 0 or 1. And that's why it's important to know it's in the p orbital, which means the only acceptable value would be L is equal to 1, which is the p orbital. And remember that these orbitals, and for the m sub L, you then go -1, 0, +1. These go -1, 0, and +1. So it is in the m sub L of -1. And lastly, it is pointing downward, which means it has an m sub S of -1/2. So again, as we talked about, you could get really, really sort of specific in terms of quantum numbers and what they are for a specific electron that's found in an atom. In addition, we talked about some sort of exceptions to the normal electron configuration, and the two really common ones that we oftentimes deal with is chromium and copper, and that's 29 and 24 on the periodic table. And really the exception here is that they will end up with argon 4s1 3d5 and argon 4s1 3d10. The exception is right here. They actually have one less electron in the s orbital, one more electron in the d orbital, and they're just found to be experimentally sort of more stable in that sort of configuration. We also talked about that if you look on the periodic table as well, actually below copper and chromium there, you will see very similar exceptions that also occur. There's even some that have no electrons in the s. They've all been sort of promoted. And the reason they're able to really do that is, again, a reminder that, for example, the 4s and the 3d orbitals, they're very, very close in energy. And what ends up happening, as we also talked about, is once you actually start putting electrons into the d orbitals, they actually switch in energy, and the 4s becomes higher in energy than the 3d. And that's why we see sometimes two things occur, but sometimes, again, as we talked about, if you sort of Google it or look somewhere else, you'll sometimes see people write electron configuration almost in order. It looks like it's like all the 3s are together, the 3s, the 3p, the 3d, and then the 4s. And that's usually electron configuration written in terms of energy, because that is truly what happens is they do switch. But in this class, and pretty much most chemistry classes that you take, as we talked about, you do basically do sort of the order of filling, and that means that the 4s comes first. But really where this plays into effect is the idea of when things basically get charges and they lose electrons. So if we took something like our sodium, which was our 1s2, 2s2, 2p6, 3s1 for sodium. When sodium, oops, no charge. I got ahead of myself. When sodium does gain a charge, it has only 10 electrons. And it loses the last electron there, which is its valence electron. And we end up with this configuration, our neons configuration. And that's what we talked about when things gain and lose electrons that are the representative elements on the periodic table. And that's our groups 1 through 8. Those guys, metals will go backwards to the noble gas that comes before them. Non-metals will gain electrons and go forward. So oxygen with a -2 versus, say, oxygen with no charge, 1s2, 2s2, 2p4. And with the charge, it actually gains the electrons there in its empty spot. And 1s2, 2s2, 2p6 also going to hit neons configuration. And again, things that have the same electron configuration as we talked about are what are referred to as being isoelectronic with each other. And for our representative elements, that's essentially what happens. But when we do get to our transition metals, because of this change in energy that occurs when something, say, like iron, for example, which is 20, what we got there, 6, I believe. So iron is 26, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. That should be 26, 10, 20, 26. When iron becomes iron with a +2 charge, it's down to 24 electrons. And unlike our representative elements where you could go to electron configuration and go, okay, it's the last ones, because of this switch that occurs with the s orbitals, it will actually always lose its s orbitals electrons first. And it would end up with a configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d6, again losing the 2 electrons here first. And that happens with all the transition metals. Again, they typically will lose their s electrons first, and then if they need to, they'll then go into the d. So if we had iron with a +3 charge, it basically be 1s2, 2s2, 2p6, 3s2. Let me just move some stuff out of my way. There we go. 3p6. And again, we would lose the 2 electrons here, and then we would still need 1 more electron, which would then come out of here and end up 3d5 in that particular case. So transition metals are a little bit different in terms of how they lose electrons, always going to be the s electrons first. And then if necessarily, they will dip into those d ones. This led us into sort of a conversation about the periodic table. And again, a reminder that we have groups. So really badly sketched periodic table here. We have group 1, group 2. We skip the middle part. And then we have 3, 4, 5, 6, 7, and 8 happening. And a couple of important areas here that we talked about. Obviously, we do this A numbering as we go across. We have our metals usually around here. By the way, there's that staircase that comes down, right? And really to the left of the staircase is our metals, right? So kind of going this way is our metals. Above and to the right of our staircase is our non-metals. The staircase is our semi-metals. And metals, right, are good conductors of heat and electricity. Non-metals are the opposite. They're dull, they're brittle. Semi-metals are guys that have properties that are both metal-like and non-metal-like together. We also talk about some similar sort of names. Group 1 is the alkali metals. Group 2 is your alkaline earth metals. Group 7 is your halogens. Group 8 is your noble gases. In this middle region between group 2 and group 3 is your transition metals. We also have those 2 groups, our rows there that are typically on the bottom. That's your lanthanides and actinides. And again, if you remember, if you kind of follow the atomic number, these 2 rows here technically should go right there. And again, that's why they're sometimes referred to also as the intertransition metals. That's where a lot of radioactive elements are and so forth when you look at it. One important thing when we talk about sort of these groups, by the way, groups go up and down on the periodic table as opposed to periods that go left to right on the periodic table. And a couple of things here. Hydrogen is usually found over here. I'll put it up here. Again, usually right on top of group 1, but it is not a member of group 1, as hydrogen is actually a non-metal, as we talked about, but again, always sort of found over here. But again, lithium is where our group 1 would start with, not hydrogen as part of it. Now, when we look at the periodic table, you know, there's really 7 periods. And that does relate to what we were just talking about, which is our electron configuration. So remember, on the periodic table, there's really sort of blocks. And our S block is groups 1 and 2, 1s, 2s. Our P block is over here in terms of electron configuration, 3 to 8. Our D block is here with our transition metals. And our F block in terms of electron configuration is down here at the bottom. And remember that we also talked about that you could, if you needed to, sort of almost count off the electron configuration just from the actual periodic table. A couple of things you do have to watch out for, again, is our D block here starts with 3D, which is 1 behind the period number, because that's on period number 4. And this is 4F down here, and that is 2 behind the period number of 6 over here, where it normally would go. So you do have to watch out for a couple of those things. Again, I would recommend, like we talked about, that you use sort of the zigzag approach. That's usually pretty a good way of doing that. And we sort of finished up, started talking about the periodic table and stuff like that. We talked about some periodic sort of trends and stuff like that. And when we talk about periodic trends, again, just kind of looking at our periodic table, draw a big one, maybe. Try to get some stuff out of the way here. Hang on a sec. There we go. A couple of important trends we talked about. First off, for example, we had atomic size. So the size of the atom as you go left to right on the periodic table there. Draw a better one here, maybe. All right. So as we go left to right on the periodic table, atomic size decreases, right? Gets smaller and gets larger as we go this way. So atomic size increases as we go down. We also talked about the idea of ionization energy in terms of the periodic table. So ionization energy is the energy required to remove an electron from the gas phase. So basically forming a cation, and that increases as you go up and to the right and decreases as you go down. We also talked about electron affinity. Also increases as you go up and to the right and decreases as you go down. And we also threw in there electronegativity. Remember the difference between electron affinity and electronegativity. Electron affinity is the energy change that occurs when an atom gains an electron. So remember we talked about ionization energy, sort of the energy involving the loss of an electron. Electron affinity is sort of the energy change when somebody gains an electron, becomes an anion. Electronegativity is the ability of an atom to bring electrons towards itself. So electronegativity increases as you go up and to the right, with fluorine being our most, which is obviously way up here, not down there. But, and also decreases as you go this way. And what this all sort of helps us understand is what we sort of talked about, that with all these sort of periodic trends happening, typically what we would expect to happen is metals will typically lose electrons and become positively charged, or what are referred to as cations, while nonmetals, which are typically upper right of the periodic table, will gain electrons, become negatively charged, and are known as anions. So these periodic trends really do help us sort of understand why we see those certain things, why we see are metals typically losing their electrons, while our nonmetals are typically gaining their electrons in those processes. So that also ties into the idea of cations and anions and sort of the periodic table. So we'll go back this way here. Remember that when we think about the periodic table and we think about charges that are associated with certain things, everybody in group 1 has sort of a fixed charge. When it does make a charge, it's going to be +1. Everybody in group 2 will be +2. Group 3 will be +3. Usually aluminum we're talking here. When we go above the staircase and nonmetals, starting in group 5, -3 is typically the charge, -2 for 6, -1 for 7. And transition metals have a pretty much variable type of charge that's associated with them. But there are like a group of transition metals. I'm going to draw them lower than they are. They're actually up here, up on top. But just to give me a little bit of room here. Zinc, cadmium, and silver, again, right about here on the periodic table. This sort of backwards L. Zinc and cadmium, although they are transition metals, no matter what the situation, will always make a +2. Silver will always make a +1 charge. So those are the typical charges that we sort of associate with these guys when they do make charges. That then brought us into talking about basically bonding, and that helped us sort of understand, hopefully, some of the bonding stuff that we talked about. And when we talk about bonding, there's really two types of bonding we talked about. We talked about ionic bonding, which is always a metal and a non-metal. And important in this type of bonding is what we have because of those periodic trends is a transfer of electrons from the metal to the non-metal. That's going to make our metal become our cation, which is positively charged. That's going to make our non-metal become an anion, which is negatively charged. And again, there's absolutely no sharing of electrons here. It's that electrostatic attraction. That basically will hold those together. Remember that the larger the positive negative charge, the stronger that attraction will be between those two guys, and they'll basically hold it together stronger. So what that means, again, is if you have a +3 and a -3 that comes together, that bond is going to be much stronger than, say, a +1 and a -1. But they'll still be held together, but absolutely no sharing of electrons here. And that's different than covalent bonding that we talked about. In covalent bonding, that is typically two nonmetals. And the difference here is we do have sharing of electrons. And in this case, the sharing of electrons may be equal, which means it's a nonpolar covalent bond. Or it may be unequal. So some unequal sharing of electrons, which is known as a polar bond. So remember, we can have those electrons being shared equally or unequally, resulting in either a polar bond or a nonpolar bond happening. Ionic bond, again, really no sharing of electrons, just a full transfer. So when we talk about that, we talked about really Lewis dot symbols that can help us sort of understand that. And also going back to our periodic table here, the number of valence electrons for our representative elements equals the group number. So everybody in group 1 has 1 valence electron, everybody in group 2 has 2 valence electrons, and so forth. So if we did something like, say, the formation of sodium chloride, sodium is group number 1, which means it has 1 valence electron. Chlorine is group number 7, which means it has 7 valence electrons. And in terms of sort of configuration-wise, our sodium is neon 3s1. And our chlorine at 17 is neon 3s2, 3p5. And what's going to happen here is, again, we're going to get this electron to transfer over. I'll just draw it this way. When it does, the sodium then becomes positively charged at that point. When it loses its electron, the chlorine again gains that electron and becomes negatively charged. So as we talked about, when we do draw these sort of structures for ionic compounds, you should include the charges, because this implies that there's no sharing of electrons, which is why we also sometimes will see brackets sort of involved. The effect on the electron configuration is when sodium loses that one electron, it ends up with 10 electrons, and neon's configuration, the chlorine gains that one electron in its p orbital and moves forward and now has 18 electrons, which is the same configuration as argon. And if you remember, that again is the whole point of bonding, is for everybody to achieve the same electron configuration as a noble gas. And by metals and nonmetals, when they come together, the way they're able to achieve that is by gaining and losing electrons that allows them to reach that noble gas configuration, which is really stable. That's because our noble gases are group 8s. They're chemically inert. They're just perfectly happy with the way they are, and they're very, very stable. Now, when we talk about sort of covalent bonding, again, when we have those guys that come together, like, for example, two fluorines, they are going to share electrons, as we talked about. And really the reason for that is, if you think about the periodic trends that we talked about, all the nonmetals are all pretty much sandwiched together up here in the periodic table, right? Except for hydrogen. But all the nonmetals are pretty much sandwiched right up there in the upper right corner of the periodic table, which you see that all these trends pretty much end up in the same spot, upper right, which means everybody that's a nonmetal will share very similar periodic trends in terms of ionization energy, in terms of electronegativity, electron affinity, which means unlike metals and nonmetals, which are on opposite sides of the periodic table and have very, very different sort of periodic trends, when nonmetals get together, because they have very similar ones, the best that they're going to do is decide we'll share electrons. They both really want the electrons, but because they have very similar sort of properties, nobody could really take the electron from another person. So the best they could do is share. And in a case like this, we would expect these electrons here to be shared. Could be represented with a line there, or you could use all the dots all the way around if you want. And remember that when we look at this, there's two types of electrons. There are these guys here, which are non-bonding electrons, are sometimes referred to as lone pairs. And then there also is obviously the electrons that are involved in a bond, which are known as bonding electrons. Now, when we sort of count the electrons for everybody, they're going to share these electrons in the middle. So all 8 of those electrons count for the guy on the left, and then all 8 of the electrons count for the guy on the right, including the 2 that are shared between them. They both end up with those 8 electrons being shared. And in terms of bonding, that is an important rule. That is what is known as the octet rule. That also would put both of these guys essentially in group 8 territory, which is our noble gases, and they're very, very happy in that sense, right? Everybody really wants to get to that octet rule to become very stable through the sharing of those electrons. But in terms of getting back to the type of sharing that we would expect here, we would expect these electrons to be shared equally. And that is, again, because the fluorine is going to pull the electrons to the right. The fluorine on the other side is going to pull it back to the left. And since they're both basically the same, they're going to pull on those electrons equally. And we're going to get an equal distribution of all these electrons, which means this is a nonpolar bond, covalent bond. And that's different than if we did swap out a fluorine for a hydrogen like we talked about. And again, you can represent it both ways. If you like all dots, you can. And in this situation, same thing here. The fluorine here is going to get its 8 electrons. The hydrogen here actually is going to share a pair of electrons, giving hydrogen 2 electrons and giving fluorine 8 electrons. And that's okay for hydrogen because that's all it should have. And that is sometimes what is referred to as the Duet Rule. Because again, if you look on the periodic table, hydrogen comes right before helium. And helium is a noble gas that comes right after hydrogen. Helium has only 2 electrons, which is why hydrogen should only have 2 electrons. It should never have more than 2 electrons. Everybody else needs pretty much 8 electrons to be really happy. But the difference here, though, in terms of the sharing of those electrons, there is a difference because in terms of electronegativity, fluorine is the most electronegative element you could have. Remember, it has a value of like 4. And that means that when the electrons are in this bond, the electrons are going to head towards the fluorine, which we could represent with this little dipole arrow. And this dipole arrow points to the side that's more negative, and the side over here that's more positive is at the side where it points to on this. And basically what that does in something like HF is it creates a partially negative charge on the fluorine and a partially positive charge on the hydrogen. And this sort of unequal sharing of the electrons is what is known as a polar covalent bond, or just a polar bond is sometimes referred to. And again, that results in sort of that unequal sharing of electrons. So how do we know if it's going to be equal sharing or unequal sharing? We can use those electronegativity values to help us with that. And if you remember, electronegativity values, as I just mentioned, runs from 0 to 4, 4 being the most electronegative, 0 being not so much. And really, if you had a bond, you essentially would just subtract the two numbers. So I believe, let's see here. I believe hydrogen is 2.1. I'm going off the top of my head. And I think this guy is 4. So if we do the difference in electronegativities, give or take a point something, 4 minus 2.1 gives us a 1.9 difference in terms of electronegativity. And that would imply a polar bond because we had certain cutoffs. So if you remember that if the difference in electronegativity was 0 to 0.4 is considered a nonpolar bond. If it's kind of above 0.4 to below 2, it's a polar bond. And usually above 2 is a ionic bond. And so here at 1.9, that's pretty up on the top end there, but it's a polar bond. They're still hanging on and still being shared, but very, very unequally being shared on the fluorine side, basically hogging it there. So we could use sort of that Pauline's electronegativity values to help us understand if we're dealing with a polar bond or a nonpolar bond. To be honest with you, as we talked about in terms of ionic bond, you really don't need the electronegativity values because pretty much if you see a metal and a non-metal present, you should know it's going to be really an ionic bond and no sharing of electrons. But really, we do use electronegativities to help us determine really this. And what we're talking about here is, again, what is referred to as bond polarity. Not to be confused with molecular polarity, which we'll talk about as well. We talked about in a later chapter. But bond polarity here is that using that difference in electronegativity values to help us understand sort of what type of bond we're dealing with. And this led us to sort of talking about actually drawing Lewis structures for covalent compounds and Lewis structures for covalent compounds. Really, you want to follow some rules when you do it. You want to make sure you get the right skeletal structure. You want to count up the total number of valence electrons. You want to make a single bond from the center atom to each outside atom. You then want to put the non-bonding electrons on the outside atoms first in pairs until you fill up all the outside atoms with that octet rule 8. And then if you still have left over, then you want to go to the center atom and put it on in pairs. And then lastly, you want to check for the octet rule being met. And if it's not, that is where you want to typically double bond or triple bond to fix it. So as we talked about, usually you don't want to necessarily double bond or triple bond right out of the chute there. You do usually want to kind of save it for a situation where you might need to fix something that may be incorrect. So for example, again, if we looked at NF3, so nitrogen is 5 valence electrons. There's 3 fluorines, each has 7. That is 26 valence electrons. Remember that when we're trying to figure out the logical arrangement, the least electronegative atom will find itself in the center. Hydrogen should never be in the center because it should only have 2 electrons. And if you put it in the center, it's going to have more than 2. And fluorine should never find itself in the center because, again, it is the most electronegative atom. So this logical arrangement would work. You could put the fluorine on top like we talked about, a single bond to each. We have now used each line is 2 electrons, 2, 4, 6 electrons gives us 20 to go. We're going to put it on the outside until each one has 8. And at this point, we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We use 24 electrons on the outside. We still have 2 more to go, which then would go onto our center atom as pairs as well. And again, if we look at the center guide, 2, 4, 6, 8 is good. All the outside ones are the same. They all have 8, so they are good. Again, if you had something like CO3 2 minus, like we talked about, carbon is 4. There's 3 oxygens at 6 each. And we would add 2 here for the charge. Again, the minus means that it gained electrons, so you need to add that. If you had something with a positive charge, you need to subtract. And if we get all that there, that is 24. Carbon should go in the middle as it is the least electronegative there. A single bond to everybody. That is 2, 4, 6. Again, 8, 10, 12, 14, 16, 18, 20, 22, and 24. At this point, we have used up all of our electrons. We need to make sure everybody's good. So 2, 4, 6, 8 for all the oxygen is good. The carbon, though, here is not good. It has only 6. So this is the point where we would want to fix it by making a double bond to try to fix it. The reason we can't just put electrons there is now we would have 26, which is too many. You also cannot just drop the double bond in there for the same reason. You will end up with too many electrons. So remember that when we do make a double bond, we need to take away, we need to take away a pair of electrons and bring them in. And in this case, all the oxygens are the same, so it doesn't really matter which one you do. So I'm just going to take it from the top. So I'm going to erase them from up there. We're going to bring the electrons in to make that double bond. And typically, if it has a charge, if I don't keep hitting the wrong button there, we put some brackets around it and a -2. And if we look now, we have 2, 4, 6, 8 for the double bonded oxygen, 2, 4, 6, 8 for the single bonded oxygen, and our carbon now has 2, 4, 6, 8 electrons. Everybody has 8 electrons. We still were able to maintain our 24 total electrons, and this would be the correct one. We also talk about this sometimes when you do a double bond like this, because there's options as to where you could put it, we could have double bonded the left-hand side. We could also double bonded the right-hand side instead. And all three of these structures are what are sometimes referred to as resonance structures, which are sometimes sort of drawn better than I just did there, but also usually represented by these double-headed arrows in between them. And they're resonance structures because those double bonded electrons are delocalized and they're sort of moving around. So at any given point in time, they may be to the left, they may be to the right, but they are sort of moving. And you know, so any one of those structures would be perfectly fine to draw. If you're asked to draw all the resonance structures, then technically you should draw all three of those. Any questions on any of that stuff so far there? All right, so hopefully this is helping, I hope. Do you want to continue this in lab? Yeah. So we'll probably continue for a little bit in lab, kind of doing the same path here. And we'll do that in about 20 minutes, I think, yeah. Okay, so I'll see everybody, I guess, in about 20 minutes, and we'll continue, maybe continue on with some of this lecture. I don't know the whole 3 hours, but we'll do some more. All right, I'll see everybody in a bit.